G'day chemistry students. In this video, we're looking at dot point 6.2.2 and focusing on some basic calculations involving pH, building on what we already learned about from last lesson. Let's get into it. Now, the first thing that I want to look at to help us sort of explain some of the calculations that we're looking at today is the self-ionization of water. Now, the formula for it is not in your formula sheet. In fact, it's an equilibrium that we're looking at. So using the same kind of equilibrium concepts and rules that we looked at in module 5, but we've actually been given a K value for the ionization of water at 25 degrees Celsius. It's 1 times 10 to the neg 14. Self-ionization of water is referring to this equilibrium that can happen for any type of water in any solution. Could be pure water, could be in solution, but the idea is that a very, very, very small amount of water molecules will actually interact with each other and act as an acid and a base. One will accept a proton, being the base, and one will donate a proton, being the acid. And that's going to form hydronium and hydroxide. Even when you have just pure water, deionized, all the ions removed, this process still happens in very small amounts. And this equilibrium is characterized by this K value. So we can write out an equilibrium expression. Kw is equal to the concentration of the hydroxide times the concentration of the hydronium. And that is equal to the Kw value of 1 times 10 to the neg 14. We can then solve for this equation because these guys are going to be equivalent. We can just do a quick square root. And what that means is in water, in regular conditions, the concentration of hydronium is 10 to the neg 7 moles per liter, and the concentration of hydroxide is 10 to the neg 7 moles per liter. For those who are a little bit more mathematically inclined, at this point, you could apply our pH equation and find that that reflects a pH of 7 exactly, where water is perfectly neutral. However, what we find is when we add acid or base, there's going to be a shift in equilibrium. If I add hydronium ions to a solution by adding acid, there's going to be a left shift, which will reduce the overall concentration of hydroxide. And the amount of hydronium which is reduced is very negligible. On the flip side, if we add a base and maybe consume some of this hydronium, then there's going to be a left shift. And that left shift is going to be leading to a reduction in hydronium ion concentration. So what we'll find is if we have an acidic solution, there's going to be an imbalance of hydronium and hydroxide. There's going to be a lot more hydronium versus hydroxide. And essentially that means that the concentration of hydronium exceeds that 10 to the neg 7 moles per liter. For an alkaline or basic solution, we would see the opposite, that hydronium concentration has essentially reduced. In that case, the hydronium concentration will be less than that neutral point, 10 to the neg 7 moles per liter. And for a neutral solution, we'll say that everything is completely balanced. We'll have a pH of 7. The hydronium and the hydroxide will both have a concentration of 10 to the neg 7. We can sort of see this relationship begin to develop between this hydrogen and hydroxide concentration. As we become more and more and more acidic, there's less hydronium present. And as we become more and more, there's less hydroxide present, I should say. And as we become more and more basic, there's more hydroxide and less hydrogen. What that means is that you can use the Kw equation to calculate the concentration of either the hydroxide or the hydronium if you already know what the other concentration is. That will make a lot more sense when I show you that in a practice calculation. There are a couple more equations to go on with. If we're looking at the concentration of hydroxide being a thing within these calculations, that means that we can also put the concentration of hydroxide onto a very similar log scale and determine POH. And now POH is equal to neg log base 10 of the concentration of hydroxide. It's pretty much exactly the same as a pH calculation. We're just substituting in hydroxide concentration instead. Similar thing as well, we can convert the concentration of hydroxide to a POH value. What should also be known as well, and it's got to do with this sort of increase-decrease relationship here that's got to do with the self-ionization of water. What we also need to keep in mind is that pH and POH always adds up to 14 in a solution. So we're actually able to use all of the equations that we've learned about in the last couple of lessons to calculate for any of the values that we've been looking at. So I've drawn up a little bit of a flow chart to show that they are all interconnected, and you can undergo a series of calculations using those equations to convert from one value to the next. So for example, if we're converting between concentrations, hydrogen ion, hydroxide ion, we can use our Kw value and our knowledge of equilibrium equations to apply this value here, solve for the unknown. We can convert between pH and pOH by using pH plus pOH is equal to 14. We can also convert between P values and concentration values by using our two sets of log-based equations. Now let's get in and do a couple of practice questions using these concepts. For this first question, we're being given the pOH of lemon juice, which is 10.5, and are being asked to calculate the hydrogen ion concentration of the solution itself. Now we can use the flowchart, which we've looked at this lesson, to be able to convert between all of our values. So in this question, pOH is our starting point, and hydrogen ion concentration is where we want to end up, which means that we can take two routes. We can either calculate pH and then calculate the hydrogen ion concentration, or we can calculate hydroxide ion concentration and get to hydrogen ion concentration. In this one, the route that I'm going to be taking is through pH. Generally speaking, if I'm moving from one corner of this flowchart to the other, I usually like to pick the pH-pOH conversion because the equation is quite simple. So what we do first is identify our starting point, pOH, which is equal to 10.5. We can then write the equation pH plus pOH is equal to 14 and rearrange to solve for pH. So pH is equal to 14 minus pOH, which is 14 minus 10.5, and that's equal to a pH of 3.5. From there, we need to be using our hydrogen ion concentration equation to be able to calculate from pH. So that's concentration of hydrogen ions is equal to 10 to the power of negative 3.5. Put that into our calculator, and we should find that that is 3.2 times 10 to the negative 4 moles per litre. Moving on to our second question for this video. Slightly different, but using the same concepts and flowchart. 2.35 molar solution of lithium hydroxide prepared, and we're being asked to calculate the hydrogen ion concentration of the solution. Now, given that we have a concentration and we know that we're working with a hydroxide, it should be pretty quick and easy to find the hydroxide ion concentration from that information. We'll have to just do a quick check of our molar ratios to see whether or not this is the concentration of hydroxide or whether we've got to double it, half it, etc. What we're being asked to find though is our hydrogen ion concentration, and that is our endpoint in our flowchart, meaning that there should be only one step required to calculate the hydrogen ion concentration. Once we know the hydroxide ion concentration, to use that, we'll be using the dissociation constant for water. So what we'll do first is write out the formula for lithium hydroxide. Lithium has a charge of plus and hydroxide has a charge of minus. They balance each other out. So lithium hydroxide exists in a 1-to-1 ratio. So LiOH is its formula. Knowing that, we should be able to determine quite quickly the concentration of lithium hydroxide should be exactly the same as the concentration of hydroxide, because we have one hydroxide for every lithium hydroxide unit, which means that the concentration of hydroxide in this question is going to be 2.35 moles per litre. All we then need to do is calculate for the hydrogen ion concentration. So we know that Kw is equal to our hydroxide ion concentration, which we already know, multiplied by our, and you can either put hydronium or hydrogen ion concentration here, H3O plus or H plus is more than suitable. They are interchangeable terms. We can then solve for H plus, and that's equal to the Kw value, which is a known value in your data sheet, divided by the hydroxide ion concentration, which we calculated previous. So we know, if I look really closely, Kw is 1.0 times 10 to the negative 14. We're also going to be assuming that we're working in standard lab conditions because we haven't been told otherwise. So that Kw value should hold 1.0 times 10 to the negative 14 divided by a hydroxide ion concentration, which is 2.35. We can then put that into our calculator, and that is equal to 4.3 times 10 to the negative 15 moles per litre, or molar. And I have one final question for you. Again, similar kind of question, different process. Here we're being told that we have 1.5 grams of sodium hydroxide. There probably shouldn't be an there, that's a bit of a typo, but 1.5 grams of sodium hydroxide is being added to 50 mils of water, and we're being asked to calculate the pH of the solution. So with the information that we've been given, we should be able to use these two terms to calculate the concentration of the sodium hydroxide, NaOH. I'll just acknowledge here as well that the sodium and hydroxide are in a 1-to-1 ratio because sodium's plus and hydroxide is -1. So we're going to be able to find the concentration of sodium hydroxide using that. We're going to be able to take that value and quite easily convert that concentration to the concentration of hydroxide. So that again is going to be our starting point for this question. What we're being asked to calculate though is our endpoint here, the pH of solution. That's this guy here. So again, we can take two paths. Both of them are pretty reasonable. I'm going to be taking this path in particular. Just, I guess, a personal note, I find using this equation a little bit more effective, foolproof, quick, and easy as compared to the Kw value equation that you can also use. But that's complete personal preference. I'm just going to be using this method for this question myself. So what we can then do is first calculate the concentration of sodium hydroxide. So concentration of NaOH is going to be equal to N over V. Now, we don't know N yet. We've been given a value in grams, which is a mass. So we also need to do a quick number of moles is equal to mass over molar mass. So first off, the number of moles of sodium hydroxide present in the solution is going to be equal to 1.5 divided by its molar mass, which is 39.997, 0.38 moles. We can then use this value and substitute that into our concentration equation. So the concentration of NaOH is equal to 0.38 divided by our volume. So we have a 50 ml solution, remembering that we've got to put this in litres because we measure in moles per litre. So 0.05, 0.75 moles per litre for that one. So using our formula for sodium hydroxide, we can also make the statement that the concentration of sodium hydroxide is the same as the hydroxide ion concentration, which is 0.75 molar. We can then start working with our flowchart now that we have our starting point, our hydroxide ion concentration. So we can go from that hydroxide ion concentration to POH by writing up the formula here, this one here. POH is equal to neg log 10 of our hydroxide ion concentration, which is neg log 10 of 0.75. Just put that into my calculator really quickly. Keep in mind too, I am carrying my numbers in my calculator the entire way through. It's a little bit hard to show in video, but it is something that I am considering and doing. So that's 0.12 is the POH. What we can then do is calculate pH from that. So the we know that pH plus POH is equal to 14. We are trying to solve for pH, so I'm going to make that the subject. So that's 14 minus POH, which is equal to 14 minus 0.12, and that comes to be roughly 13.9. And there we go, a few different ways of using our big pH, POH concepts and calculations to do some reasonably complicated calculations, especially considering that a lot of these equations are not explicitly in your data sheet. So it might take a little bit of practice, but once you get these basic tools sort of set in stone, it's going to mean that we can start doing some much more complicated problem solving as a result. Thank you very much, everyone. In the next video, we're going to be doing some more advanced pH calculations. But until then, have a good one.